All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. It's friggin' snowing outside again. It is snowing outside. I mean, the forecast has like 2-digit numbers in the next week, and I'm delighted about that, but it's snowing again. We'll get there. We'll get there. It's kind of like that time of year where it's like the end is in sight. It's there. I can see it, and I'm just like, nah, snow. All right. By the end of today's lecture, the only thing that I really want you to be able to do is describe what happens in various parts of the system when a segmentation fault happens. This is going to touch on a lot of things. We're going to be taking a look at virtual memory to start, yes, but we're also going to be working our way back to things like shells and processes and inter-process communication. I don't want to give anything away, but we're going to be touching lots of parts of the course in this one lecture to have a vague sense of what happens when we get a segmentation fault. What I want to do to start is just remind ourselves what exactly is segmentation. And then I want to have a bit more of a formal definition of what a segmentation fault actually is in the context of what segmentation is. So the grand idea of segmentation is that rather than allocating an entire address space, and this is what we were doing with base and bounds, rather than allocating an entire address space, we allocate only parts of our address space. So with base and bounds, we were partitioning physical memory. With segmentation, we're partitioning virtual address spaces. And we're only allocating the parts of the virtual address space that we're actually using. So we're not allocating the entire segment. We're only allocating enough to say this is the code in the heap right now as it is right now. We might grow these segments later. We might say you're calling malloc lots. My library will do something. We'll investigate this next class, but you're calling malloc lots. You're trying to make your heap bigger. So I'm going to make that segment a little bit bigger in physical memory. We might change this at runtime, but initially we're only allocating as much as we are actually going to use. And the structure of this kind of turns into something like this, where on the left side, we're partitioning physical memory and we're putting entire address spaces into memory with base and bounds. But we've got this main problem of internal fragmentation. On the right side and in the middle, what we're doing is we're partitioning our virtual address space and then putting into physical memory only the segments that we're using and only as much of the segment as we are actually using. The strategy that I'm showing here in the middle for partitioning our virtual address space is partitioning this into 4 segments. In practice, we're only partitioning into 2 segments as opposed to 4 segments. The 2 segments that we're partitioning into in practice are going to be the code and heap section. Once we allocate the code section, we never change its size. The only time that this would change is if we were to do exec. And at that point, we're allocating an entire new virtual address space for the process. So the code segment size never changes once it's allocated. The heap is something that does change. And so we can kind of just put the heap and the code together in the same segment and then allow the heap to grow. And then the stack itself is down here at the bottom in its own separate segment. So in terms of practical segmentation here, we're really only going to be using 1 bit to indicate which segment something is in, whether it's the code heap segment or the stack segment. But the structure is still the same. I'm only going to allocate as much of the code heap segment as I'm actually currently using in my process, and I'm only going to allocate in physical memory as much of the stack segment as I am actually currently using in my process. As time goes on, it will be changed. I will grow it, I will shrink it, possibly, and then eventually I will discard these things from physical memory from my operating system perspective, but I'm only going to allocate as much as I am currently using in each of these segments. These 2 words in Comp 2160 very quickly became a frustrating experience because in terms of this is the first time you're working with C, segmentation fault, no additional information, full stop. I'm not really sure where to go with this because I can only see the word segmentation fault showing up on my screen. And unlike Java and Python, where I've got these nice friendly stack traces, segmentation fault does not even tell me what line number this is happening on. I have no additional information. Segmentation fault is something eventually we figure out that we can use our debugger to help figure out why we're getting into this state, but it's still kind of like unclear why we're getting into this situation in the first place. A segmentation fault is formally defined here as when I try to read or write a virtual address that has not been allocated by my process. So I'm gonna quickly move back here. In terms of my heap, in terms of my stack, and in terms of my code section for this process, that would mean that I'm trying to work with a virtual address that's like somewhere in here. That virtual address has not been allocated by my process. That's like trying to access something in this region. This is a virtual address that has not been allocated by my process. That's like asking to access or use or read or write something that I thought might be part of my heap, but is actually here and has not been allocated by my process. To be clear, our process can ask the OS, please make my code heap section bigger. And then at that point, I will have allocated these virtual addresses. But the segmentation fault here is coming from the fact that I'm trying to allocate or I'm trying to use this part of the stack segment that I haven't actually allocated in my process. So when my hardware is then trying to translate this virtual address that's out here in the middle of nowhere to something that's actually in this allocated region for my stack, it's going to very quickly figure out, you know, that isn't actually part of the stack segment that is currently allocated by the operating system. And so I should raise an exception. I should raise some kind of exception. So our segmentation fault here is that I'm trying to read or write in a virtual address that has not been allocated by this process yet. Usually, this is null. Usually this is null. And in my abstract diagram, I'm putting the code segment up at 0, at address 0, but in practice, when we were looking at that maps file, my code segment starts at like some crazy number like 55F, whatever. It's quite a big number. Virtual address 0 is not allocated by my process. Virtual address 0 has not been allocated at all by my process. And so really commonly, we're getting these segmentation faults because we're trying to access, dereference, or otherwise use, read or write address 0, but virtual address 0 has not actually been allocated by my process. Let's write some very bad code. I want to write some code that does this, that causes a segmentation fault to happen intentionally. I put a piece of code as a starting point up on the course webpage in the virtual memory Git repository. So I've linked to this Git repository if you want to follow along. The file that I've added to this repository is called segmentation faults. And as it stands right now, this code fails to fail. It runs to completion. It succeeds. It does not currently segmentation fault. So let's make it segmentation fault. I'm going to start by adding a pointer to an integer that's called something, and I'm going to assign it the value of null. I'm going to do a printf here, and I'm going to say that the value at of something is %p. %p is a way that I can print out the address of something. I'm going to have to cast this to void pointer because printf is assuming that the pointer that I pass to it is a void pointer. I'm expecting this to print out null or nil, null or something like nil. Any of those things are what I would expect this to print out, and this line will work. I expect that this line will work the way that I'm expecting it to. Then I'm going to say, oops, because the thing I'm going to do next is not going to work. It's going to not work in the way that I expect it to not work. I'm going to now try to dereference this value. I'm going to leave exit success here because I want to think optimistically. Yeah, it's going to get there, and it's going to succeed. Yeah, you can do it, process. I believe in you. I'm going to save this code. I'm going to write it. I'm going to quit. I'm going to run segmentation fault. It has failed successfully. It has failed successfully. On line 12 here, what I'm saying is, I'd like you to take the address that's at this thing, and I'd like you to read it, please. And if we remember looking back at, I'm going to do proc self maps here. Address space, the address space mappings here do not have address 0 allocated. They don't have address 0 allocated. Our code segment here starts at, in this case, 5ABE something. It's quite a big number, but address 0 is not allocated by this process. And so when I try to dereference it, I'm going to get a segmentation fault because I'm trying to access an address in my virtual address space that has not actually been allocated by my process. So, segmentation faults. The reason these words are being printed out is because we're trying to access some address that hasn't actually been allocated by our process. My question for you, and there's only one question. This isn't a quiz. I'm looking for your opinion on what you think about this right now. The words segmentation fault, core dumped, are being printed by somebody here. And I'd like to know from you who you think that is. I'll hold this up for about 5 seconds, and then I will switch over to the Mentimeter. It's not a quiz, so it's not a huge race to get to answering this question. All right, I'm going to pop over to the Mentimeter. There's people already answering. I'll hold this question here for, I don't know, 10 more seconds to give you a chance to answer. All right, everybody in the classroom has answered, or at least that's the same number of people in the classroom right now. Okay, so awesome. I'm going to begin by making an assertion that it's not the hardware. The hardware is definitely part of this whole process. The hardware is absolutely part of this whole process. And the hardware, in terms of the role that it's playing here, is I recognize that this virtual address has not been allocated. Based on what the operating system has told me about the address space for the process that's running right now, the address that is being requested is not allocated by this process. I want to give this some spiritual credit in the sense that if we still had hardware that was typewriters, yeah, literally the hardware would be typing out the word segmentation fault. But for what we're looking at right now with the terminal, it's not the hardware. So we've got the OS, the standard library, and your program being the main contenders after that. And so let's find out. I am going to start taking us through some Linux kernel source code. I want to begin, before I even open this link, by emphasizing that I will not ever ask you about Linux kernel source code. I'm not going to ask you questions about the source code that we're looking at. What I'm trying to do with this process is give us the overall idea of what's happening at the operating systems level, but I'm not going to ask you like hyper detailed questions about what the Linux kernel is actually doing, because that's not actually important. it is super cool because we're going to see stuff in the Linux kernel that looks almost like what we're doing right now in this assignment, and that is awesome. But I don't actually care that much about Linux kernel source code. So keep that in mind. I'm going to pop open this link. You are more than welcome to follow along with me if you want. I really like this website, and we have seen this a couple times before. I really like this website because it makes it pretty easy to get around the Linux kernel. It makes it easy to like click on a function name or reference and then see where that thing has been defined in many places. So it's easy to go from a function is being called here to its implementation is over here without having to know the relationship between all these C files. There are a lot of C files in this repository because it's a very big piece of software. So having something like this helps a lot. The very first place that we're going to go is in this Arch folder. The Arch folder represents architecture-specific implementation details. So the folder names that you see here represent the different architectures that the Linux kernel currently supports. So there's architectures like Alpha, which is something that comes like quite a lot before us in terms of architectures. Then there's stuff like ARM. This is Android running on your phone, is running the architecture stuff that's in this, this set of directories. There's M68K, which is baffling to me as still being in here, but M68K is like classic Mac, you know, the one that's a box shape. If you've been in my office, this is the one that's on my table. This is a 68K processor that's in here. There's PowerPC, there's Spark, but the one that we're currently running is x86. So my laptop is an x86 laptop. If you're running a Mac, you're probably running ARM as opposed to x86. But for the most part, if you're running Windows or Linux, you're running with x86. So we're going to take a look here. And then the directory that we're going to go into from this is include. And then the folder that we're going to go into here is ASM. And ASM here is assembly. It's assembly. We're not going to be looking at x86 assembly. I don't want to look at that. We're not going to look at x86 assembly, but there are headers in here that are important for what we want to take a look at. So the file that I'm going to take a look at is down here under I, and it's this IDT entry. IDT entry is the place where we're filling up all of the interrupt descriptors for this architecture. We're not looking at where the OS is registering these things, but we're going to look at what the OS is doing in terms of these are the interrupt descriptors. These are the functions that you should call when something happens, when a fault happens. So at the very top of this file, what we've got is a bunch of these preprocessor directives that will have things like declare IDT entry and then ASM linkage, and then some preprocessor magic that is these number signs. This is doing like string processing with the preprocessor. The really important parts of this are that this ASM linkage here, this says that there is assembly somewhere in this directory structure that represents what this thing is going to be. We're just going to hand wave that. We're not looking at x86 assembly here. The main thing that I do want to look for is the word fault. So I'm doing Control F, and I'm typing in fault, and I'm going to scan down here, and I'm going to go all the way to the very bottom, or very close to the very bottom. And the thing that I want to see is what I've got highlighted here right now. So this says declare IDT, whatever, raw entry error code. And then it says x86 trap PF. Trap, that's the keyword that we recognize about what the OS is doing when it brings the system up. It's saying the trap table for, or the trap table entry for this thing or this event is you should call this function. And so the function that we want to invoke here when we have this trap that is whatever underscore PF is, and I'm going to give away a little bit of something here and say that it's not segmentation, it is page fault. In reality, we're not doing segmentation. We're actually not doing segments at all. modern architectures, anything that's older than 40 years old hasn't been doing segments. Segments have not been used for a long time, but the path that we're taking through here is going to be related to this idea of a page fault. We'll look at page faults next week in our classes that we've got, but it's enough to say that it's the same pathway through the Linux kernel for both of these things. At this point, what I would normally do with this Elixir website is copy this and I would paste it into this search field. But the problem with this, and I can't explain why this website is not working the way that I'm expecting it to here, is that it doesn't find it. And I don't really know why, but I know where this thing is. So I'm going to open up the file that this is contained in. I'm going to zoom out just a little bit so that I can get my whole screen back. I'm going to go to the root directory of the kernel, and I'm going to go to, and I've typed this all up because I don't want to mess this up. I'm going to go to Arch again, x86. This time we're going to go into a folder. The folder is MM. This is memory management. And the file that we're going to look at is called fault.c. I'm going to search for that string, and we can see it show up way down here at the bottom. Is it text big enough at the back for you to see? Okay. Is that better? Okay, awesome. So way down at the bottom of this file, we have the definition of the function that we've got here. The thing that jumps out to me immediately that is super cool is that we're getting an address. We're getting an address of something. There's hand-wavy assembly stuff that's happening underneath this, but we're getting an address of something. We're in the process of handling a fault, and we're going to get the address that has caused the fault to happen here. There's some other stuff that's happening related to KVM. KVM is related to virtual machines in the Linux kernel, so we're just going to ignore that that is happening here. And we're going to go all the way down here to handle page fault. I'm going to click on this one. This is it's defined in this file as a function. And immediately we can see some kind of cool stuff here. We're declaring instances of struct task struct. We're declaring instances of these structures that are named VM area struct and MM struct. VM, virtual memory. MM, memory manager. So we're starting to build up a relationship between the virtual addresses that we've got and the physical addresses that we've got. This line right here, this is something that you might have something like in your own code for assignment 3. Current here is the currently running task. It is the currently running task. And this is not a file scope variable. There's a lot of magic that's happening with the word current showing up here, but it's getting the currently running task. And we're taking a reference to that thing, and we're assigning that to this pointer that is TSK. I'm going to scroll down here, and we're in the middle of handling this page fault. And there's stuff that's happening, like enabling and disabling interrupts. Now, this is thinking us back to locking. If we can disable interrupts, that's the same as locking. That is the same thing as enabling a lock. I'm going to acquire the lock by disabling interrupts. You can't interrupt me, so I don't really need to do any locking because there's nothing that's going to interrupt me. The local part here, I believe, don't take my word for this, I believe that the local part here is for this CPU. So don't disable it for all CPUs, but disable it for the current CPU that this task is running on. I'm going to keep scrolling down here, and ultimately what I'm going to get back to is this line, bad area, no semaphore. Bad area, no semaphore is saying that we've tried to access, so area here, that is that VM area that we were looking at, virtual memory area. I'm trying to access something that has not been allocated in one of those things. So I'm going to click on this. And I'm going to go to the x86 implementation of this. This is not an interesting definition of a function, so I'm just going to immediately follow this to the underscore variation of this. On the very first line there, I'm getting current task again. So we're not passing the task around between these functions, but every function is getting that task for itself. And there's an important comment right there. I will read it aloud to you. It says, user mode accesses just cause a sig seg v. Sig. Sig. Sig is the key acronym here. Sig. It's causing a signal to be sent to my process. It is causing a signal to be sent to my process. And I'm going to scroll down here, and on line 825, it says force sig fault sig seg v. There's a void user address. Here's the address that caused this fault in your virtual address space. Handle this signal, please. Handle this signal, please. I'm going to click on force sig fault. And I'm going to importantly point out now that the things that we're looking at with forcing faults begin to touch our scheduler. And forcing signals to show up begin to start touching our scheduler. We've got to tell a process that it has a signal, and that really is part of the scheduling process in this system. I'm going to do the implementation of this, though. So the definition on line 1701 of this signal.c in my kernel directory here. I'm going to follow this because it's not an interesting function by itself. I want you to notice what we're populating in this structure right now, where we've got this SI underscore prefix of this structure. And I want you to think back to what we were doing with signals and populating our own sig action variable and how it kind of resembles what we're doing with this population of this kernel sig info variable. I'm going to click on this. I'm going to take a look at the comment above it. And the comment above it is telling us things like, force a signal that the process cannot ignore. So if it was sig ignore, remember that we have these default values for signal handlers, and we can set a signal handler to be sig ignore. Just, I don't care about this signal. I don't want to process it. I don't want to do anything with it. And then we have these sig defaults, the default signal handlers. The default signal handler for sig seg v is to jump core and exit. If we took a look at the manual page for signal, section 7 of the manual pages for signals, it would describe this action as dump core and exit, the default for signal handling. If I scroll down here a little bit, and I start to take a look at the structure that we've got here, T here is going to be the task that we are currently working with. So it has been passed to this function as an argument. Sig hand, this is the table of signal handlers for this process that we're starting to take a look at in the process of starting to work with sending this process a signal. I'm going to keep scrolling down here. And on line 1319 is where we're sending the signal to this process. I'm going to take a look at this definition as a function. I'm going to scroll down here a little bit more to send signal locked. I'm starting to skip over lots of stuff because now I don't actually care too much about what's happening with all of this. Ultimately, what we're getting to is if we get all the way down to, this is an interesting part here where we're doing allocating signals in a queue for the process, which tells us that when we send signals to a process, they get queued up in the operating system level. So sending one process a signal doesn't cause it to just complete that signal handler, but it may cause others to queue up behind it. And then eventually what we get to down here is the complete signal function, which is then going to start taking us really into the scheduling stuff. And at this point where we've got signal wake up here, we're definitely getting into the scheduling stuff. And I'm really delighted to stop here. This is going to be the part where our scheduler will begin to do things like context switching and switching over to the process, and then letting it know that it has this signal for it to handle. I would like you all to note that throughout that, the words segmentation fault, core dumped never appeared anywhere. They did not appear anywhere. And that was pretty much the entire path through. The interrupt has happened all the way to we're going to start scheduling another task. The word segmentation fault never ever appeared there. And so what I'm going to do now is I'm going to go in the opposite way. I'm going to start at the shell. So the shell here, in our case on Aviary, is TC shell. And when I run segmentation fault here, remember the stuff that we're doing with this is we are eventually going to be calling fork or clone in the case of Linux and exec. I don't know why I'm trying to do this way. I'm going to do -e trace is equal to %proc. Process. Yeah. So in this case, we're calling exec VE on this program, and we're asking that program to be executed. So we're trying to change the address space for this process to be in there. So it's the shell's responsibility ultimately to cause our process to begin to run, and it's the shell's responsibility ultimately to then wait for our process to finish. So my next stop is going to be to take a look at the source code for TCSH. I'm going to be looking at GitHub here. This is a mirror of the repository for TCSH. And some of the things that I thought was interesting about this immediately was stuff like this, that this file was committed and last changed 34 years ago. TC shell is a very old piece of software. I believe I can confidently say that with the exception of me, this is older than everyone in this room. I believe I can say that. This is an old piece of software. I'm going to start by taking a look at some of the code that's in this shell. And I'm going to go down here, and what I want to take a look at is sh.proc or sh.exec, proc.c. I'm going to take a look at sh.proc.c. I'm going to close this symbols tab, and I'm very quickly going to stop looking at sh.proc.c because this is a huge disaster. This is like 40 years of preprocessor directives that are testing for every possible variation of operating system that this code runs on. And it's unreadable. I don't find this to be any kind of readable source code. It appears to be a functional shell. I can run programs with it, but I cannot read the source code for this shell. Instead, what I'm going to do is I'm going to go back up to the top here, and I'm going to start searching in this repository for the words segmentation fault. And, right, damn, forgive me. There we go. There are the word segmentation faults. It appears in a few places. One is this file that's called set2. It's under this directory that's called C. C here is a language. So this is a language mapping file. It's not C, the programming language. It's C like the canonical language that gets used on systems. And in this case, it happens to be English. So this is what it's using to try to do translations for things. So you can run TC shell using languages other than English, like whatever language you might want to run TC shell under. The other file that I want to look at is here, sh.init.c. And the thing that's important to me about this sh.init.c is that on line 349 here, it's got segv. And this is the suffix of the signal number that we were looking at that was generated by the Linux kernel. And we can actually see the words segmentation faults here. That's important. I'm going to click on this identifier here. And what this identifier is going to do for me is take me to other files where that identifier is used. And in other places where this identifier is used is in sh.proc.c, which is ultimately responsible for calling functions like fork and exec. I'm going to click on this line, on line 1103, where it's beginning to inspect the reason why this process appears to have stopped. And I'm going to scroll up. I'm going to scroll up here, and I'm going to note that it's asking a question about why this process has stopped. There's a switch on this status variable, and it says p if signaled. And we now know that the OS is actually signaling this process. You have received a segmentation fault, so you need to do something about it. But at this point, our process has exited. If I keep going up here, I'm going to get to a point where what we're doing in this code is starting to take a look at, sorry, I need to stop somewhere else. I'm going to go back to where we were. I'm going to click on p reason. I want to see where this is populated. Yes, this is what I want to see here. We're calling these weird looking functions that are w stop sig, w term sig, and w exit status. And if I scroll up from here, what we're going to see as I move up from here is that we're calling functions like wait. And we're calling functions like wait PID. We're calling functions like wait and wait PID. So our shell has launched our process. It's called execve. It called clone or fork. It called execve. Our process is doing something. And our shell is sitting here waiting for our process to exit. I'm going to pop back to my terminal here. And I'm going to open up the manual page for wait. And here's the definition of the two functions that we would have been working with for our assignment, wait and wait PID. And if I scroll down, what we're going to be able to see is that there are these other function-looking things that we can call to ask questions about after the process has exited. So after we return from wait, why did it exit? Was it signaled? And what was the signal that caused this process to exit? What was the signal that caused this process to exit? And so our shell waits for our process to exit, see that it received a sigsegv. The default action for sigsegv is to dump core and exit. Wait in the shell returns. And our shell asks, hey, why did this process exit? Was it signaled? And what was the signal? And based on that, it is able to print out for us segmentation fault, core dumped. segmentation fault core dumped. And I'm going to quit my manual page here, and I'm going to run fish. Fish is the shell that I normally use on my laptop. I'm still on Aviary, so I'm still connected to a machine on Aviary, but I'm running fish in this shell. And if I run segmentation fault, you may have seen my shell when I run code like this on my own machine printing a different message. And it's because it's the shell that's printing this message out. That is, yes, I am so happy that we can go from this point of, in comp 2160, segmentation fault, Y, to now, page fault. There's some kind of exception happening with virtual memory. I'm trying to access an address in my virtual address space that I have not asked my operating system to allocate. My process is running on the processor. The operating system has told the processor, hey, when you're looking up virtual address translations for this process, these are the ranges that are valid. When I try to dereference null, which is 0, that address is not allocated in my virtual address space. And so there's an interrupt. There's a fault that happens. The hardware says, hey, this process just tried to translate this address, this virtual address, into a physical address that has not been allocated by it. I'm going to go to that interrupt table, and I'm going to start calling the function that handles the interrupt. The interrupt handler starts to take over on our Linux system here, on the machine that we're running. And it starts to do things like decide why have we received this interrupt from the hardware, and then eventually make a decision that it was because the process was trying to do a translation of a virtual address that it hasn't allocated in its address space. And then it starts to prepare to send a signal to that process. We go all the way through getting the signal set up, and we get to our scheduler, and our scheduler then starts to try and get this process waking up again to say, please handle this signal. The default action for SIG-SEG-V on Linux and in POSIX systems is dump core and exit. Our shell at this point is taking over again. It's regaining control of the processor because it was calling wait on the process that it launched for our process to start. And it's able to inspect the reasons why our process exited, like was a signal sent and what signal was sent. And then it's able to determine it was a segmentation fault. So I'm going to print out segmentation fault core dumped, or in the case of fish, job 1, segmentation fault terminated by signal SIG-SEG-V address boundary error. Yes, yes. Now we know what's going on when the words segmentation fault are printed to our screen. We don't have to be happy about it, but we know the path. We know what's going on in the OS. We know what the hardware is doing. We know what our shell is doing, and we know kind of all the different parts that are happening ultimately underneath all of this. We've got a couple minutes left, and so my last question for you is, if it's a signal, can I handle the signal? When we were working with signals before, we had certain signals that we couldn't do anything about. The certain signals that we could not do anything about, I'm scrolling way down here to get to this point. Were the kill signal. You can't ignore this. You're exiting, you're done. This is me telling the OS, you've got to terminate that process. I can't handle it. I can register a handler for it. I can apparently register a handler for it, but it can't do anything. But what about SIG-SEG-V? Let's try. Keep in your mind what you think right now. I'm going to do the simpler implementation of signal handling here. So this is the version of our signal handler that only takes one argument. So I'm not putting like the sig action stuff in here. I really just want to register a very simple signal handler. So the function call here is going to be, I want to say signal, I want to say sig seg v. I want to register a handler for that, and I want to pass to it handle signal. I'm going to quit this. I'm going to make it, I've got to include signal.h. I'm going to quit, I'm going to make predict the output here. Just take a second, think about this. I appreciate that you're sticking your hand up and wanting to answer, but just stick it in your head for now. Are we ready? Are you ready? Is this what you expected to see? My immediate expectation would be it prints out handling signal and exits, or it doesn't do anything, or it just seg faults. What's happening here, I'm going to hit Control-C, I'm going to terminate this. What's happening here is I did print this out. I did print out that the value of something is nil in parenthesis. I did print out the word oops. That did appear at the very beginning of the output here. And then I got to this line, and this line does, it's a bunch of different stuff. Like when we're thinking about assembly language instructions, there's many different things that are happening here. But ultimately what we did with this part was we called load on null. We're asking to get a value from null, which is 0, 0, 0, 0, 0, with 64 zeros here for our address. The hardware recognizes, yes, that's not an allocated address in this virtual address space, raises that interrupt or that fault or that exception. The OS sends the signal to our process. The OS sends the signal to our process, and we start handling the signal. And we print out handling signal 11, handling sig seg v. And then our signal handler exits. Signal handling, remember, is we're putting a stack frame wherever you are right now. And when this stack frame gets popped off, you're going back to wherever it was you were before that stack frame got added, which was the instruction load null, which then causes a fault and then causes a signal to be sent to this process, which starts the signal handler and puts a stack frame on the stack, and then it prints out handling signal 11, and then we exit the signal handler, and then we go back to that instruction, and we try to load 0, and then you see where I'm going with this, and you saw the output of this program. It's just going on forever. So yeah, we can handle seg faults. We can handle the signal that gets sent to us with seg faults. We can't do much about it. We could exit gracefully. We could do, like, if we're trying to write something to a file and we're in the middle of that write, we can say sync the file, persist things to disk and close it, and then exit, and then call the exit system call. I want to terminate my process now. At this point, you should be able to describe what happens in various parts of the system when a segmentation fault happens. You should be able to describe what happens in terms of the words segmentation fault are actually appearing on my screen, and you should be able to describe like who's responsible for the different parts of getting to the point of dereference null to segmentation fault core dumped is showing up on my terminal window. That was an exciting ride. Thank you all for coming along with me on that ride. That's it for today. I hope that you have a great rest of your day, and I'll see you all on Friday. Bye, everybody.